X with it. We're gonna double tap this zombie right here.
Imagine we have a spherical conductor with a cavity inside of it, and in that cavity you have kept a positive charge. Let's say imagine it's floating in air over there, okay? And it's not at the center right now. The question you want to try and answer is this. See, this positive charge is going to start producing an electric field. And that electric field is going to start sucking the electrons from this metal. Remember, metals have free electrons. They can
Take our
move
time.
under
I
the
can do
influence
this
of
real
electric
fast.
field.
We can do
So as a
this.
result of that, electrons will get sucked in, and so there will be
Try
some
not
negative
run
charge getting
ultraviolet
induced
right
over
now.
here. As a result of that, there will be some positive charge getting induced on the outer surface.
And just
And
regular
as a result
sunshine.
of that, our electric field is going to get
visible light.
modified. So the question is, once all the electrons have stopped moving, once we have reached electrostatic condition, we have to answer three questions. What would be the total charge on the inner surface and how the distribution would be? What would be the charge on the outer surface and how the distribution would be? And what would the new electric field lines roughly, the sketch of that, how would that look like? So these are the three questions we want to try and answer. So how do we do this? Where do we even begin? This looks like a very complicated, challenging puzzle. Well, what I like to do, let me first dim the electric field lines a little bit. Alright. So what I like to do is go back to one of the basic things we've seen about conductors and electrostatics. We've seen that in electrostatic conditions, conductors should always have zero electric field inside of them.
Right.
Why? Because if there are any electric fields over here, they will start pushing on the electrons and the electrons will start moving. That means we are not in electrostatic condition because electrons are moving. So whenever we are in electrostatic condition, automatically it means that there are no electrons moving. Automatically it means that the electric field must be zero. And if you need a more refresher on, on this concept, we've talked about this in great detail in a previous video on electrostatic shielding. So feel free to go back and check that out. But anyways, let's come back to our question. We know because of this electric field generated by the positive charge, it's going to start, sucking in negative charges.
Well,
so
right now we took a step. We're going to get the curveball and putting it into orbit here in a minute.
And because our conductor is neutral, if there are some negative charges which are induced over here, because of that,
they're actually allowed out of it. Things are not the hydronic lighter here, and we'll get into that. We'll show
and our goal is to figure out how much these are.
Okay. Remember, because understanding this gives you this, this is a better... They've been running it, and we'll get into that here in a minute.
So let's start with the induced inner charges, the purple charges, negative charges.
Right.
How much would that be? Would it be equal to negative Q? Would it be more than negative Q? Would it be less than negative Q? Or do you think it's possible? Do you think there is not enough information? We'll not be able to calculate that. How do we do this? How do we figure out how much these negative charges could be? Well, at first it looks like, how do I know? Like, how would I know in the electrostatic situation exactly how much of the negative charges would come? Maybe it depends upon the position of this charge. Maybe it depends on the strength of this charge. I don't know for sure. So how can I calculate
if people thought a ball wave,
we can
we're going to get into that. Remember that statement. People, mathematicians and other things. This is an important topic about how to set up some stuff. I'm going to show you in a minute. And he's also going to do.
How do I figure out exactly how much? What is the connection between charges and electric field? Ooh, Gauss's law. Gauss's law is the one that connects charges and electric field. So why don't you pause the video and see if you can somehow use Gauss's law to figure out exactly how much negative charge should be induced
Let it be light, huh?
So why don't you pause the video and think about that? So what I would like to do is I'm going to choose a Gaussian surface and make sure that Gaussian surface, the entire surface, choose a sphere, but the entire surface lies within the bulk of the conductor. So imagine this is my spherical Gaussian surface. Now because I know that under electrostatic conditions, electric field everywhere over here is zero.
Well, if you do like it, like if I say the word hydronic lighter, this is one thing to do, but let me fast forward here for you. Let's see.
Which means that the total enclosed charge must be zero. And from that, I think I now understand how much this negative charge should be. If the total enclosed charge should be
put
zero,
that thing
and I already
into orbit,
have plus
man. I'm
Q,
telling you.
that
This curveball right here about the calling balls and strikes. When I show you the strike zone.
So this should be
it's right there, and right at the moment I'm going to put that photon into orbit.
Zero. And what's amazing is that it doesn't matter where I position this this little q. It doesn't matter where I move it, total induced must be negative
right
q.
now,
And
Nemesis,
therefore the total induced
the
on
universe
the outer
at large, trying to put
should
this
be
thing
plus
around
q.
the cycle for
because we know that the conductor
coulomb
is
and
neutral.
Newton meters.
So if there is negative q inner induced on the inner surface,
forbidden S&P
plus
order,
q must
right?
get induced on
what
the outer
element
surface.
are we using?
So the charge on the outer surface is plus q, the charge on the inner surface is
Kelvin.
negative q. And so what's interesting is whatever charge we introduce inside, automatically that charge gets manifested on the outside. Wonderful, isn't it? That's an amazing thing about a conductor. But we're not done yet. We also need to look at the charge distribution and what the electric field looks like. What the new electric field is going to look like. So let me bring back the original electric field. Here it is. So this would have been the electric field at the beginning before all of these charges got induced. The question is, what would this new electric field look like? Let's do this in steps. Let's first look at the electric field in this region. What's going to happen to that? We know that electric field has to be zero in understanding electrostatic conditions. So we can go ahead and rub that. So let me do this. This electric field is going to disappear.
Well, they also invert square.
Alright, so we got one part solved. The next question I want to try and answer is, how would the new electric field inside look like? Would it look exactly this way? Would it just look like this, or do you think it's going to change? Again, can you pause the video and think a little bit about this?
This is him putting it up to the scopes and stuff online to the light bulb. He changes light bulbs to check their frequency,
Again, something that we've
get
talked
zeroed
about in
from
videos.
the general
But
relativity
because our
that
conductor is an equipotential surface,
will do
that
this. And
means
again,
the
this is
electric
right-hand
field over here must
rule,
always
90
be
or what is it, 120,
to
240.
the surface. And you can see that these electric field lines are not over here.
If classroom students had to
which means these
get this
electric
to
field lines are
tap
going
in the
to
right
bend
tap
in such a
to
way that they
turn
try
the
to
orientation
be
of the
perpendicular wherever they meet the
on-off
surface.
binary.
So the way it's going to look like, again, it's a rough figure. The electric field lines are going to bend somewhat like this, from positive to negative, but they also always ensure that the angle between the field lines and the inner surface is going to be 90 degrees. Alright, I have another question for you. How do you think would the charges get how would the charge distribution look like? Do you think it's going to be a uniform charge distribution over here, or do you think there's going to be, some part is going to have more concentration while some part is going to have less concentration? Again, can you pause the video and think about how the charge distribution would be on the inner surface, this negative q? Alright. So because the charge is closer to this surface, and you can see the electric field lines over here are stronger, and they're close to each other, and the electric field over here is far away, and which means it's weaker, we can immediately guess that there should be more charges over here and there should be less. So you would have stronger charge distribution. I know it's a little hard to see, but there should be more charges on this side and there would be less charges on this side. So charges will get more concentrated over here, charges will be less concentrated over here. Alright, final question. How would the outer charge distribution look like? Would it be uniform because it's a sphere? Or do you think it's going to be, there'll be more positive charges over here because there is more negative charge over here, and there will be less positive charge over here because there is less negative charge over here? So, final time. Can you pause and think a little bit about how would that be? Alright. Now when I first thought about this, I thought, yeah, because there's a lot of negative on this side, there would be a lot of positive over here, lot of positive charge over here, and there should be less positive charge over here, right? But think about this. There is no electric field in between. The outer charges are sort of disconnected from what's going on inside.
Camp 1, Camp 2, Camp Lejeune, the baby, the
Which
bathtub,
that the outer charge distribution is absolutely
at a most, the new statue of the Kiss, the new Kiss of Death statue wave function is usually what I go with here. But if you got one of these,
therefore the outer charge
identity
does
and
not depend upon the inner charges.
Again, some of the
only depends upon the geometry, and because it's a sphere, we've already seen before, because of the symmetry, the outer charge distribution has to be uniform, and as a result, this electric field is also going to change slightly. Remember, this electric field now appears to be coming from this charge, but because we have a symmetric uniform charge distribution, the electric field is going to be radial, so it's going to appear to be coming from the center. And so the new electric field, outer electric field, is going to be radial. What I absolutely love about this problem is it's really challenging, but to answer that, we just needed the core of this is going back to the basics that in electrostatic condition, electric field inside a conductor must be 0.